Good afternoon, everyone. We might get started today. I know there's still people joining, but hopefully they can catch up. My name is Josh. I'm a PhD student here at UQ. I'm the current head of the SFP student chapter here at the University of Queensland. And today we have a colleague who has recently joined us, Dr. David Morrisset. So David has just joined us, and he's a lecturer in fire safety engineering at the University of Queensland. He's recently finished his PhD from the University of Edinburgh, where he investigated the topic of flame spread over solids. Prior to starting his PhD, David worked as a consultant in many different fire engineering firms, such as Jetson Hughes in the US, Arup in the US, and Red Fire Engineers here in Melbourne, Australia. Some of David's passions in his research area includes quantifying material flammability, looking at different upholstered furniture testing, combustible cladding, high performance mass timber, and especially layer diagnostic tools. He is a current member of the SFP internationally, a National Fire Protection Association, and the International Combustion Institute and International Association for Fire Safety Science. Today, David will be presenting some of his work about characterizing fire growth and how we can relate this to some industry practices. Without further ado, I'll pass the microphone over to David to get started.
Right, thank you, Josh. Just give me 2 seconds to switch over my screen. Can everybody hear me online? Thumbs up. Cool. Excellent. All right, one moment, folks. Okay. Excellent. Thanks for the thumbs up online, everyone. Appreciate it. Hello, everyone. Thank you all for being here today. Thank you for joining our SFP session for the student chapter here. Thank you to the SFP chapter for having me. I appreciate you, everyone giving me, extending the invitation. So my name is David Morrisset. I'm a lecturer of fire safety engineering here at UQ. Josh gave a very great introduction, so I appreciate that. But today I want to discuss the concepts of fire growth and flame spread, and particularly how we might use these as fire engineers in engineering analysis. So the rate at which a fire grows is sort of a critical consideration for fire safety engineering, right? So how do we basically, the point of the talk today is really to look at how do we leverage our knowledge of fire dynamics and fire safety science to sort of better shape our use of growth rates in our actual engineering work. Now, before we get too far into this, I do want to take a moment to acknowledge country. I want to acknowledge the traditional owners and custodians on the lands which we're streaming from today. I pay my respects to elders past, present, and future. I recognize the enduring connection of Indigenous communities to country, and I extend my respects to any Aboriginal or Torres Strait Islander people who might be joining our call today. So a little bit of background on me. Josh actually did an excellent job sort of kicking this off, but for anyone who doesn't, who might not have heard me present before or wondering who this guy is, I am relatively new to the Australian research community, so it's exciting to be here. But for a little bit of context, I did my bachelor's and master's in California, Cal Poly San Luis Obispo. I just completed my PhD at the University of Edinburgh in November of last year. And since then, I've been a lecturer in fire safety engineering, so coming up on my 7th month here at UQ. And also, as was mentioned in the introduction, before my PhD, I had industry experience working as a fire engineer, both in California with Jetson Hughes and Arup, but also with Red Fire Engineers here in Australia. So the goal of today's presentation, right, if we can summarize it and sort of hit the punchline right away, is really to discuss fire growth rates in the context of a design fire analysis and to link those growth rates to fundamental physical drivers, right? So I'm going to use that term physical drivers and fundamental phenomenon throughout this presentation. But an example of what I mean by that is understanding how do we contextualize things like growth rates in the context of flame spread, right? Flame spread is a very specific fire phenomena, and we can use that to provide some context behind things like fire growth rates and heat release rates. So that's sort of the objective of today's presentation. To briefly sort of rattle through a presentation outline, we're going to start with a little bit of background. We're going to look at what is fire growth, how do we characterize things like fire size. It's typically a discussion of things like the using heat release rate curves, what is an alpha T squared growth curve, those kinds of things that I think a lot of engineers will be familiar with. I'll briefly discuss some fundamentals on flame spread. This is not a dedicated flame spread lecture. I would love to give a 2 hour dedicated lecture to these kinds of things, but we'll keep this within the context of fire growth. And then lastly, we'll look at things like heat release rates for complex fuel packages. How do we actually characterize things like fire growth? And then we'll touch very briefly on how do growth rates and the framework that we have for fire growth, how does that change as we look at things like emerging hazards and new things that we're seeing in fire safety engineering. So just to kick things off, right, in a range of fire scenarios, the hazard of a given fire is largely linked to this process of fire growth, right? So it's this idea of transience that a fire will grow that makes fire so particularly hazardous, particularly in the context of things like considering occupant safety. All of these things require a transient analysis of fire growth, right? So this concept applies to fuels that you might see in a typical building fire. Things like upholstered chairs, so our typical fuel loads. This also relates to things like exterior fires on things like cladding systems on the exterior envelope of a building. But this concept also applies when looking at things like fire growth in, say, a bushland environment and looking at things like the wildland urban interface, right? The hazard of a fire will evolve as that fire grows, right? Now, this rate of growth is often linked to this concept of flame spread, right? Flame spread is not the only thing that drives fire growth, but if you can think of the idea that fire will grow to consume fuel nearby, and therefore that mechanism by which a fire will spread to other fuel is an intrinsic part of this concept of fire growth, right? So that's one that we're going to focus on in particular detail today. Now, this idea of flame spread being linked to fire growth and fire growth being linked to fire hazard can be relevant to all sorts of conditions, right? This could be relevant for compartment fires, it can be relevant for exterior building fires, and it can be relevant for things like bushland fires, right? However, we're primarily going to focus our presentation today on compartment fires, right? The typical kind of fuel loads that we'll be looking at as fire safety engineers. Not to say that these principles can't be applied elsewhere, though, right? Now let's take a look at the framework of what we'll say is our design fire analysis, right? So when we're doing something that requires us to assume a design fire, right? At the heart of that process really lies our assumption of a heat release rate, right? So there's different ways we can define a design fire. You can use temperature time curves for structural calculations. You can use all sorts of other assumptions. But really, when we're trying to characterize fire behavior, the heat release rate, right, is our best metric for fire size, right? So that will become an intrinsic implication in so many bits of analysis that we might do, right? And you see that by looking at all the kinds of analysis we might do in fire dynamics. But in order to choose a design fire heat release rate, you sort of have two choices, right? Let's say two coarse choices. One, you can choose an idealized type fire. Let's get my laser pointer out. You can choose an idealized configuration, such as an alpha T squared fire. Can we see that online? No, that's okay. I'll go without it. Or you can choose something from real data. You can run an experiment. You can actually conduct an experiment on a fuel package and look at the heat release rate of that particular fuel package, right? But regardless of the choice that you choose, that heat release rate will be essential in conducting additional analysis, right? And again, I keep saying that heat release rate shows up in lots of different ways. But if you take any calculation you might find in, say, a textbook or the SFP handbook, whether it's ceiling jet correlations, right, for things like, say, if you're trying to do a sprinkler calc or just understand the temperature distributions along a ceiling, whether you're looking at entrainment rates for something like two-zone modeling, or whether you're looking at what's the critical flashover threshold, my heat release rate, right, all of that will link to the heat release rate. And another essential sort of analysis to consider is if we're going to do anything with CFD, if we're going to be running an FDS simulation, we need to be able to prescribe a heat release rate, right? So I think it's very clear, though, that this heat release rate really is at the heart of these kinds of analyses, right? So the definition of our heat release rate, and for a lot of analysis, the definition of how we define that growth rate becomes extremely significant in this analysis that we're running. So I said there's sort of two course choices, right? Let's talk about sort of an idealized fire scenario, and let's talk about an experiment, right? That was actually conducted. So here we have a heat release rate curve that has an alpha t squared growth rate. So that's again something that I'm assuming a lot of people are familiar with. It's this idea that a fire might grow with a t squared dependency, and we can tabulate some sort of alpha coefficient. This will actually go into a lot more detail in the next few slides. But you have a growth rate up to a peak heat release rate, and it stays there until the fire decays, right? On the other side, you can have an actual fuel package. This is an upholstered chair that I burned under a calorimetry hood over at the University of Edinburgh, and this is the actual heat release rate output that you'll get. So if you ignite that fuel package and you let the fire grow, you can actually measure that transient fire size, right? And with all the peaks and troughs and all the transients to it. But that's a very specific case, right? That's the heat release rate that occurred for that experiment compared to something that perhaps could be a little more generally applied, right? Such as something like an alpha t squared growth rate. But in either case, right, how do we define this sort of growth rate? Like, can we characterize this, and how do we use the information of that growth to a peak heat release rate? How can we use that information as an engineer, right? In what ways can we actually incorporate that into analysis, right? And that's really the heart of what we're trying to get at today. So again, I've been throwing around this terminology of alpha t squared fires, right? And I assume that many fire engineers are familiar with that term, with what that actually means. But I want to go into a little bit of the sort of context and sort of the historical setup of the alpha t squared framework, right? So basically, the alpha t squared heat release rate curve assumes that our fire will grow as a t squared or a time squared dependency, right? And then we can calibrate that using a different alpha coefficient, right? So from things like the SFB handbook and other resources, you'll be able to find things like tabulated growth rates for what we'll call a slow, medium, fast, and ultra fast fire curve, right? Now, these are all very actual coarse sort of approximations, but really what they're approximating is these are categories where they took effectively how long does it take for that fire to reach 1 megawatt about. It was actually, I think, 1050 in the original literature because it was a conversion from BTUs. But it's about a megawatt, right? And in this case, a slow fire would take 600 seconds, and an ultra fast fire would only take 75 seconds, right, to hit that approximately 1 megawatt threshold, right? So that's the idea behind this framework, right? But where did this actually come from? And so there's quite a range of codes and standards internationally that you can look at to sort of provide some basis for this alpha t squared relationship, particularly in a design context. Just picking an example, I'm going to reference NFPA 72. This one actually has quite a bit of information behind the process of developing an alpha t squared fire. And it's an interesting reference to maybe take a look at and read through some of the commentary. But what's interesting too is if we start with this definition from NFPA 72, we'll say that a fire, if we're developing a heat release rate, fires, research has shown that most fires will grow with a power law dependency, right? It's an interesting starting point. So we're saying that fires generally grow as a power law, right? If you look at a fuel package in a room, probably won't grow linearly, but it'll grow with some sort of power dependency, right? Now, in the context of most design standards, what then the simplifying assumption becomes is we can take experimental data, take a bit of a leap, and let's reduce that power law dependency to a t squared relationship. The data that's provided in something like NFPA 72 shows that there's a lot of examples that you can find where when you burn a fuel package, that heat release rate will grow with something like a t squared dependency, right? So that becomes a nice simplifying assumption. So long as we can calibrate that alpha value, we can actually develop a generic design fire growth rate. And that's sort of the philosophy behind this, right? But it all stems from this idea that there's a power law dependency for most fire scenarios. And we're assuming that the fuel packages that we're interested in are going to grow with a t squared dependency, right? And that's kind of where it stops. And then also NFPA 72, for example, goes on to provide tables and tables of information on different fuels. So if you choose, like, let's say you want wood pallets stacked 1.252 meters high, right? You can then back out what would be the alpha classification for that fuel package, right? If I'm looking at other things, let's say, I don't know, what's another one? Polyurethane mattresses, like you can actually back out an alpha value for those, right? And so from this information, in theory, an engineer can take that our fuel load and develop an approximate growth rate, right? That's kind of the philosophy behind providing this information. And there are tables like this not just in NFPA 72, but in various resources in the fire safety literature. But it's an interesting question, though, that I'll pose, right? Is this enough information to really define our growth rates for design conditions, right? As an engineer, for all scenarios that we might design for, is simply prescribing the fuel load enough, right? There is a lot of value in understanding the range which these fuel loads give us, but are we capturing the whole picture? Is there something else we should be thinking about? Or at least, what's the limitation of this table? At what point do we need to consider some additional information, right? Because really, the choice in our growth rate makes a huge difference in the analysis that we might run. And just to show a quick example of that, let's take a range of heat release rate curves, right? And these curves were produced in a paper referenced there by Ball. But all of these curves, right, they have different growth rates, different peak heat release rates, but each one of them actually has the same total heat release, right? So based on a given fuel load that might be in a compartment, each one of these can be a valid heat release rate curve for your fire. So to speak, each one of these could be a valid design fire based on its prescribed fuel load, but each of them have very different growth rates and peak release rate behavior. Okay, so how would these different curves behave in something like a simple analysis? So let's put these fires in an arbitrary space and let's run a two-zone model, right? Very simple, nothing fancy. But if we put each of these design fires into a two-zone model, you'll see that the descent of that smoke layer, right? So by basically producing smoke and creating an upper layer of smoke that will descend, that descent of that smoke layer will vary significantly depending on the curve that you choose, right? But each one of these curves shows a valid design fire for a given fuel load. But what's also more interesting is if you follow the curves from the steepest growth rate on the left there, so start with that blue curve, then go to that orange and yellow, you'll see that that also follows the fastest descent of the smoke layer. So it doesn't matter, irrespective of what the peak heat release rate was. And again, they all have the same total heat release, but it's that growth rate that significantly affects the rate of descent of that smoke layer, significantly, as you can see. So whenever we're doing analysis, particularly for life safety, whether it's looking at tenability or analysis looking at, say, alarm detection and suppression calculations, right? These growth rates are incredibly important, right? So while we have these broad categories of understanding fast versus medium fire growths, right? Changing those things slightly makes a huge difference in our analysis, right? So how do we gain more confidence in what growth rates we might choose, right? How do we actually build more confidence in being able to actually adapt this to the scenarios that we're looking at, right? And that's really what we want to dig into a little more detail. So let's take one big step back, right? We've been talking about alpha T squared fires, and so far the basis that we understand is that in NFPA 72, there's a lot of data that's presented that shows that it's a decent fit to a T squared type dependency, okay? But can we provide a better physical basis, particularly for a time squared dependency, right? Because fires grow in all sorts of funny ways, right? So what's up with this T squared time dependency in particular? So let's start with a very simple example. Let's take something like a mattress, like a polyurethane foam mattress. Let's ignite it at one point and watch that flame spread radially outwards. Okay, so that fire is going to grow. As you can see with the schematic on the left there, that will grow with a velocity. So there is a flame spread rate as that fire grows radially in a circle, right? The heat release rate will effectively be a heat release rate per unit area. Let's call that an effective material property, right? That can be broken down further, but for the sake of this discussion, let's say that's a material property multiplied by your area. That area is growing with time, which means that you're going to end up with sort of a R squared relationship. But now let's link that radius to the flame spread rate, and you get effectively the heat release rate per unit area times some constants plus a velocity term, right? You see the flame spread rate sort of creep its way in there, and a T squared dependency. So, and actually, if you go back and there's some really interesting, particularly post-World War II literature, where sort of the early days of developing design fires, there was a lot of fire testing done on horizontal surfaces, looking at a physical basis for a T squared dependency, right? There's a lot of really interesting literature out there, particularly in a flame spread context. But basically what you do is, from a physical perspective, you take all of those parameters and you lump that into one alpha term. So by assuming an alpha T squared fire, I'm assuming, for example, one base case of that has a physical basis is a radially growing fire. That could be multiple fuel packages on a floor. That could be a single fuel package. But the important part being that we can characterize things like that rate of flame spread, because that will affect things like the actual alpha value that we assume. Now, as a simple example of how this actually works, right, here's an experiment I conducted at the University of Edinburgh. Just take a mattress, right, ignite it at one point in the middle, and that is the heat release rate being compared to the alpha t squared curves. And what do you know? It actually grows very well with an alpha t squared type dependency. What's really interesting too is if I go back and play it again, uh, take a look at what happens to the heat release rate curve up to the point where the flames reach the edge of the mattress. So the sides, there's one dimension that's shorter. It's following the t-squared dependency. Then the second it hits the edge of the mattress, it starts to deviate from that t-squared dependency because you no longer have a radially growing fire, right? So the physical basis for a t-squared dependency for this fuel package is a very good assumption. It's kind of an ideal scenario for something like a fast alpha t squared fire. It fits perfectly, right? So that is a great example of a fire scenario in which we can use something like our alpha t squared growth rates to reliably predict the growth rate of a fire. But in order to understand how this starts changing with complexity, it's worth taking a step into the world of flame spread, right? So we know that the rate of flame spread is affecting our fire growth rate for a fuel package like that, right? So what is flame spread, right? Now, the concept of flame spread was the topic of my PhD, right? So this is something that is near and dear to my heart, and I could ramble on about it for hours. The students in the room here have probably heard me ramble on about it for hours. But for the sake of this conversation, I'm going to keep it fairly limited to understanding how do we link this to fire growth, right? So we're going to largely split flame spread into two categories. We're going to look at things as either in a opposed flow flame spread problem, right? Imagine striking a match and watching it slowly creep down the matchstick, right? The flame is moving in the opposite direction of the airflow being entrained upward due to buoyancy. And concurrent flame spread. So concurrent flame spread meaning that the flame is moving in the direction of induced buoyancy, meaning like you strike a match and hold it upside down, right? That kind of effect. And so really the sort of crux of flame spread comes down to this idea that the rate of flame spread is more or less irrespective of the direction that we're looking at, right? The crux of flame spread comes down to it's an energy balance over the energy that's provided from the flame, balanced by the energy required to effectively spread that flame. How much energy does it take to actually raise my solid to the pyrolysis temperature and actually begin to decompose it? And that's balanced with how much energy can be provided by the flame to the solid, right? If I add more energy from the flame, my flame spread rate goes up. If it takes more energy to actually raise my fuel to the pyrolysis temperature, my flame spread rate goes down, right? And there's quite a bit of complexity beyond that, but for the sake of most engineering problems, we can reduce the problem to that simple equation, right? So on the simplest level, let's look at it as just an energy balance. One thing to note, though, is if we're looking at things like upward or downward flame spread, opposed or concurrent flame spread, there is a little more complexity there, right? And I would recommend for anyone who's interested in reading further, there's a great reference here by Fernandez-Peyo and Hirano that is a great review of what we'll call the controlling mechanisms. Like, what are the processes that actually control the flame spread process, right? And if you start looking into more complex things, we have to incorporate things like the kinetic rate, the reaction rate of a flame will influence flame spread, right? So in putting all of those complexities aside, we're reducing the problem, and for the sake of an engineering analysis, to the amount of heat transfer we can provide to the fuel, right? But what's interesting to note in comparing opposed flow and concurrent flame spread is for the opposed flow case, right? Let's imagine that matchstick example. If you're talking about how much energy the flame can transfer to the fuel, there's a very small area over which that can happen, right? Right at that leading edge of that candle flame, or match flame, I should say. There's a very small area over which that heat transfer is acting, right? When you're looking at concurrent flame spread, there's a much longer distance over which that flame can heat the solid, right? Resulting in very different rates of flame spread. The point being that you'll often see upward flame spread, concurrent flame spread will be much faster than opposed flow flame spread, right? For all things being equal, just try lighting a match at home and you can demonstrate that yourself, right? But the point of that being that even within the world of opposed flow flame spread, if I start changing my geometries, rates of flame spread will change, right? So these are some examples from my PhD where I took a PMMA, a very common polymer in fire safety science, and we did flame spread experiments in different orientations. So if you look at downward flame spread, and a wall configuration, lateral flame spread, again in a wall configuration, and horizontal flame spread, which that's more, I guess, akin to what we saw with the mattress, for example, right? Each of these configurations are opposed flow flame spread configurations, right? Your flame is moving in the opposite direction of entrained air at the flame front, but the actual geometry of the flame is changing in each one of these cases, right? And as you can see from the results there, the flame spread rate changes as a function of this geometry. And so because of that, it's important to know if things like our flame spread rate play a role in our fire growth, then things like, let's say I know the flame spread rate in one configuration, or I know my alpha value in one configuration. When I change my configuration, everything else changes because the heat transfer ahead of the flame front is going to alter your flame spread rate, right? So that's an important thing to keep in mind when we're looking at applying things like flame spread to practical engineering scenarios. So let's go back to that idea of the alpha T squared fire. Let's go back to that mattress example, right? So let's assume we have a horizontally spreading fire, right? And it's more, the flame spread rate is more or less constant. That's something that we saw for post flow flame spread. It's pretty, you can actually get sort of constant, steady flame spread behavior. That makes sense. So this idea of a T squared dependency starts to check out, right? We walked through that derivation. That seems good, right? But what happens if I put this mattress in a compartment? Right, so what if I put this in an actual room and we allow a smoke layer to develop? So if you put it in a room and now you allow a smoke layer to develop, that smoke layer is going to add an additional heat flux to your fuel, right? If we put this inside a compartment, it might not be the smoke layer, it could be a heated wall or an additional burning item, but there could be some sort of external exchange with your fuel. Now we assume that this alpha T squared relationship holds, but we know that embedded in that alpha is your flame spread rate term. And we also know from that very simple equation that we showed for flame spread that your flame spread rate is going to be linked to the external heat flux conditions on your surface. So if you have interaction with your fuels, with whatever else is going on in that compartment, ultimately we're saying alpha, our growth rate, is intrinsically going to be related to the heat flux conditions acting at the fuel. Meaning that alpha might not be constant in time, particularly when we're looking at fuels in an actual compartment, right? Because when we look at the data that was presented with tables and things like NFPA 72, those data were all generated for burning fuel packages underneath sort of an open space. You're burning it in an open calorimeter to actually measure the heat release rate, and you don't necessarily capture the intricacies of things like interaction with other things that might cause increased heat fluxes on that fuel package. So just at the simplest level, it's important to acknowledge that even if we have a case in which the alpha T squared model is valid and it works really well and we can get an idea of that growth rate, it is a big assumption to maintain that that growth rate will stay at that growth rate when it starts interacting with the compartment around it, right? Just something as a thing to consider for developing a design fire. But now let's forget about let's move on from something like a compartment geometry, and let's just simply change the orientation and the mechanism of flame spread. So if we go from something like this horizontally growing fire to an upward flame spread problem, let's say you have a wall of, let's say, PMMA in this example, what does that flame spread process look like, right? Now, this is an excellent paper from 1975 by Orloff and Duris. So I would absolutely recommend people go and read that work if anyone is interested in looking at the problem of upward flame spread. But what this work was able to do was to develop a sort of fundamental relationship where how do you actually look at how does the flame spread rate change as a function of time for a very large piece of PMMA. This was a very large wall for upward flame spread. And they were able to demonstrate that actually you can pretty reliably approximate the rate of flame spread not using something like a t-squared dependency, but using an exponential dependency, right? And so there's natural physical basis that when you start looking at the problem like upward flame spread, you can move to an exponential time dependency, right? And that's a better approximation in terms of the physical drivers, actually affecting that process of fire growth, right? So what can we take from that information? If you take something like a fire in a room, you start as a sort of radially growing fire. Let's say that fuel package starts in a room. It starts to consume additional fuel around it. That means in that stage, there's a very good physical basis for an alpha T squared fire. But let's say that fire eventually attaches to a wall and starts experiencing upward flame spread, right? That's where the assumption of a t-squared dependency starts to become a bit difficult, right? Because actually, your time dependency is much more fundamentally linked to something like an exponential growth rate because of the upward flame spread phenomenon, right? So that just sort of gives an idea of over the course of a compartment fire, the drivers, the things that will actually affect that growth rate might change over the course of the fire, right? So we need to sort of account for that as fire safety engineers. Now, all of that is the theoretical basis. All of that is about equations and effectively understanding where does flame spread play a role in this, right? But now let's talk about if we actually want to look at the growth rate of a real fuel package, how do we actually measure that, right? And so many people are going to be familiar with this idea, but if you want to measure what is my transient heat release rate of a couch, right? You can take that couch, you can put it beneath a furniture calorimeter, you can light it up, and you can measure the heat release rate. By capturing all the combustion gases, you can back out as a function of time, what is the size of my fire, right? Now, the beauty of this is we can take any fuel package we want and we can characterize the transient heat release rate behavior of that fuel package, right? We can get you see all those little peaks and troughs and transient behaviors of this particular fuel package, which means the results are, in one way, linked to the exact experiment you conducted, but on another way, you can use it as a method to sort of characterize lots of different fuel packages and types of materials and understand their heat release rate behavior, right? So for any engineers who are interested in finding this kind of data out there, one database that I highly recommend is the NIST calorimetry database. The researchers at NIST have done an excellent job updating this database. There's lots of information on there, ranging from heat release rate to video of these experiments. Very good uncertainty analysis and so on. It's an excellent database. Another resource to consider is if you want to look at heat release rate curves of data, you can look at the Bobrowski's chapter of the SFP handbook. Lots of very good information in there as well. And that gives you an idea. It's very easy to go out there and find information on heat release rate data, right? And I think there's a lot of value to that as a fire engineer. But when you're pulling out information, I do think it's really interesting to sort of take a step back and consider a few things when we're looking at heat release rate data. Now, this is my personal favorite heat release rate curve I've ever seen. This is from the SFP handbook. And what you can see here is this is the heat release rate of potato chips and cheese nibbles set up in a shop display, right? Now, for people who are familiar with fire testing, this is a 6 megawatt fire. That is a huge fire. That is something like an electric vehicle fire, right? So it begs the question, right? If I'm trying to characterize the characteristic heat release rate of potato chips, can I assume that it's going to be a 6 megawatt fire within 100 seconds in all scenarios? Right? That's a pretty dramatic fire. It's a really extreme growth rate in particular. That'll be a very onerous design fire for a lot of scenarios. So the question becomes instead, what was the makeup of this display, right? How was the display built? What was the materials that actually built the unit of that display? How are these fuel packages arranged within that display? Where was it ignited? Was it ignited at the bottom, so you got upward flame spread? Or was it ignited somewhere at the top or the side where you got something more like an opposed flow flame spread, right? All these things are going to completely change your design fire, right? And they will fundamentally change fire growth. So it's important to look at these things and understand that this is the integrated effect of all of the physical phenomena that drive a fire, not just these potato chips, right? And I think that's a really important point to sort of make, though. It's still extremely useful for understanding if we had more information on this kiosk, you can actually understand, okay, this is actually maybe a worst case fire size we might expect from something like that. That's extremely valuable. But then again, taking things like the growth rate with the context that it's going to be extremely situationally dependent. Another figure that's I think it's interesting from the SFP handbook is looking at what happens if you repeat an experiment. Because oftentimes we'll see heat release rate curves for a single experiment, right? That cheese nibbles kiosk or whatever was run once, right? But what happens if you run something again? Now these two curves here, I think is an interesting sort of take on this, right? Because if you ran the same experiment twice, and let's say I had only run one of those once, and let's say you get the lower of the two, and I get something like a peak heat release rate of about 100 kilowatts, right? Without running that second experiment, I would have felt pretty confident that I could characterize the peak heat release rate would be less than about 100. But simply by running the same experiment again, now I'm finding the peak heat release rate somewhere around 200. Right? So understanding that when we're looking at complex fuel packages, there's a lot going on. We need to understand why was that different, right? What were the physical mechanisms that actually led to that heat release rate being higher? And so this became a bit of an interesting rabbit hole. So I was thinking, if I take a single upholstered chair, right, and I run an experiment on it, that's the heat release rate curve I get. So I took a chair, I ignited it with a Bunsen burner. That's the heat release rate curve I get. Is that characteristic of that fuel package? If I run the same experiment again and again and again and again, 10, 15, 20 times, what is that heat release rate curve going to look like? Right. And so that's what I did. So as part of my PhD, I went and bought a bunch of upholstered chairs and we ran the same experiment over and over and over again. Right. So what we're looking at here is we're looking at a few experiments of that upholstered chair ignited by a Bunsen burner and then let to do its own thing. Now, what we'll see is that just visually, you can see that the fire growth rates of these fires are all very different. Some of them are the flames slowly spreading over the fabric of the chair. Some of them have already reached a peak heat release rate. Some of them, there's mechanical failures. The fabrics are failing. Eventually, you start seeing the chairs start to break, right? The frames themselves, the wood frames start to be involved in the fire and eventually collapse. All of these stochastic differences are going to make a difference in the heat release rate curve that you get, right? So what do the results of a bunch of experiments like that look like? This is what 25 repeat experiments on upholstered furniture looks like, right? And my favorite question to ask whenever I present this stuff is basically, is that more or less consistent than you would have thought, right? If I told you I was going to run the same experiment on something as complex as an upholstered chair, do it 25 times, with the same exact experimental conditions, same ignition procedure, everything is closely possibly the same as possible. Is that more or less what you would expect, right? And it's kind of interesting because on one hand, you see lots of scattered, right? This looks like what you might call a spaghetti plot. It's a bunch of random lines on a curve. But at the same time, you can actually see a very sort of interesting envelope of growth rates at that beginning there, right? And then you see a growth to a peak heat release rate, and then a eventual decay to, at the end, it's all just a big pile of smoldering timber, basically. Um, but there's still quite a bit of variability in time. Now, the trick being, if you take any one of those individual curves, their peak heat release rates might be as high as 200, 250. But something that we often see within the fire literature is if you take a bunch of experiments like that, let's say I take a max, a min, and a median value, right, in time. That median curve on the right there, the black dash curve through the middle, right, is in theory my average behavior of all of these experiments, right? But what's interesting is that curve no longer represents any one of the individual curves you might have seen previously. So when all these individual curves, their peaks occur at different times, right? Which means if I take an average in time, I'm truncating all of those peaks and I'm sort of smushing all of their behavior together, right? Which means that you're no longer actually characterizing that chair at all, right? And so this becomes something that, I mean, I say this because not as a, not to sort of labor a point, but we see this in the literature all the time. Experiments that are conducted on complex fuel packages like cars, electric vehicles, things like that, where we take those curves and we take an average in time. But that average in time no longer physically represents any individual experiment. So we're no longer actually characterizing the growth rate or the peak heat release rate of those fuel packages. So instead, it's really worth taking these curves and can we identify the variability using a different metric than just time? So if we take each one of these experiments and we identify a bunch of key events throughout the experiment, okay? First, let's start by looking at the actual data below. You see two figures highlighted, one in black, one in red. Those were two experiments I took as an example, right? The results in time look very different, right? So different that if I told you I had changed something between those two curves, and I think yourselves and myself would believe that whatever I changed made a difference in the heat release rate behavior. But instead, they were just the variability within repeat experiments. So as a function of time, they look very different. But if I start identifying some key events, like let's say event number 2 up there in the image is, sorry, I'll take one step back. Event number 1 is eventually once you ignite it with the Bunsen burner, your seat cushion of the chair experiences a period of radial fire growth, just like the mattresses, just like the alpha T squared fires we talked about. So the first phase is a phase of radial fire growth. Then eventually, event number 2 is when that fire growth reaches the backrest of the chair, ignites the backrest, and then results in upward flame spread. Right? So that upward flame spread results in a characteristic change from event 2 to event 3 of a rapid increase in fire growth, right? Upward flame spread resulted in a rapid increase in that heat release rate. And you can see that for both the curves. Now, in both those curves, those times just happen to occur at different times, right? But the event, the actual consequence of that event were the same, resulted in a rapid period of fire growth, right? So if you continue down the line, you can start to see that if we link up all these points and sort of, if you can, in your eye, imagine dragging point 3 and point 4 and point 5 to then intersect with one another. All of a sudden, you have a curve that actually represents a similar fire behavior, right? You actually start to capture a very general trend. And we were able to demonstrate that, where if you plot this instead of as a function of time, but as a function of these events that occur, not only do you get a much more consistent sort of average behavior of this fire behavior, and you can look at sort of this distribution of when all these times occur, but you can also sort of start to look at these regimes where in the beginning, the fire growth rate, your heat release rate, was controlled by radial fire spread over that seat cushion, a post-flow flame spread, alpha T squared type behavior, right? Then the second the backrest ignited, that new regime was dominated by upward flame spread, which means that your mechanism of fire growth is now changing. And then so on, you go through the burning process. But that's what we were able to articulate with that project was you can actually start by looking at these experiments very carefully, we were able to identify the actual physical mechanism, something like opposed flow flame spread or upward flame spread, and how that actually manifests itself in the heat release rate data, right? So the last sort of point on the upholstered furniture experiments is, let's say I take one curve, just as an example, right? And I want to sort of approximate that growth rate from the beginning up to the peak heat release rate. So there's nothing stopping me from taking this and putting an alpha T squared curve onto it, right? And actually, one could argue that that's not a bad fit, right? It follows some sort of T squared-ish dependency. Um, but there's, but again, that's not capturing the whole problem, right? Because there's more going on there than just that. It's not like the fire was just radially growing. You can see that there's clearly points that over or under predicts my growth rate, right? So instead, let's take the same data and let's sort of separate some different flame spread regimes, so to speak, right? Let's say I only fit the alpha T squared to the period which we observe radial fire growth, right? So this first little bit is when, based upon my visual observations, I was able to say that's radial fire growth. And now that fits very nicely to an alpha T squared, right? Because the mechanisms of fire growth match what we described for the mattresses. So we have a nice physical basis by which that could be an alpha T squared fire. Then there's a bit of a delay between the fire growth radially and then eventually igniting the backrest. So that causes a bit of a plateau. But then once the backrest ignites, all of a sudden we transition to a really rapid period of fire growth. That particular period of fire growth doesn't follow an alpha T squared behavior. You can just see by your eyes, right? Instead, that follows the exponential behavior we might expect for upward flame spread, as defined by that study by Orloff and Doris, right? So all of a sudden, just by making a few observations, we can then start to create a generalized curve of fire growth that is based upon the mechanisms actually driving fire growth, right? And now, like, realistically, for engineering scenarios, this might not be possible for all of our fuel packages, right? It might, yeah, in many scenarios, we'll be limited to making something like an assumption like an alpha T squared fire, right? But I think it's really important to note that by doing so, there is a huge assumption, right? You're assuming that the only process controlling that rate of fire growth is something like radial fire spread. Or instead, if we look at something, this is probably maybe a bit not too complex, but a bit complex of an example, but we can actually start to identify different periods of fire growth and we can link it to key physical mechanisms. A simpler example is maybe just looking at something like the alpha T squared model, but acknowledging that as you start getting something like a smoke layer, right, those external factors will change your alpha value, right? So it's not as simple as just choosing one alpha value and carrying on, right? Now, the last bit, I'll just take a few more minutes because I want to make sure I reserve some time for questions. But we've been talking a lot about growth rates and flame spread and things like that in the context of, I guess, what we'll call typical fuels, right? Couches, chairs, mattresses, things like that. But that's not the only thing that we deal with in the built environment, right? So under what conditions is this sort of idea of, let's say, an alpha T squared framework valid? right? Where does this start to break down, even beyond the examples that we talked about today, right? One sort of example to think about is growth rates of cladding fires, right? And again, this probably deserves quite a bit of time to go into more detail than what I have here, but effectively, if we're looking at something like the results of a cladding fire, right? The complexity of the interaction of those systems is not as simple as even already we look at upward flame spread on a wall of PMA. That's complex enough. But when we start trying to understand the growth rates of something like the interaction of a ventilated rain screen system, of various products and materials all interacting with one another, think about that smoke layer heating your alpha T squared mattress fire, and you take that complexity to a completely different order of magnitude, right? So there's a lot of simplifying assumptions that have to be made to even start approximating something like this, right? So there's a lot of embedded complexity, right? I think another example too, right, is looking at things like lithium ion battery fires, right? So arguably even more complex than trying to figure out what happens with a cladding fire. We've probably all seen videos of things like electric scooters and everything that's been going on around the world. But you can take something like a battery fire, and within a few seconds, you can go from a cloud of gas to a huge jetting flame, right? Which is fundamentally different than something like a mattress fire, right? The fire dynamics of this problem is very complex. And when you're looking at things like heat release rate curves, the actual output of your growth rate, right? These growth rates are ridiculously fast, right? The rates that we're talking about now don't even fit within the alpha T squared framework, right? These are ultra, ultra, ultra fast, right? And they don't, again, they don't follow that fundamental T squared dependency. So if we're trying to understand things like battery fires within an alpha T squared context, we need to acknowledge the fact that that framework breaks down when we look at something as complex as this, right? Understanding that growth rate requires a completely different framework. And understanding the consequences of fire spread from one battery pack to another fuel package is, again, a very complex process that isn't captured with something like the model that we currently have for something like alpha T squared fires, right? There is more complexity there that needs to be accounted for, right? Right, so just sort of to wrap things up, right? Because there was a lot of content that was covered there, but I think the sort of crux of all this is whether we're looking at something like horizontal fire spread, whether we're looking at things like upward flame spread over a wall, or whether we're looking at something like the burning of an upholstered chair, right? The process of fire growth is the consequence of all the physical phenomena, including flame spread, that might manifest themselves in that change of fire size, right? The resulting fire curve is effectively the integrated effect of all of these competing fire phenomena that then result in that fire growth process, right? So in order to reliably model that rate of fire growth for any given scenario, you really have to wrestle with some of these fundamental ideas, right? You really need to resolve what are the physical drivers that are relevant in my scenario, to which we can then pick a mathematical model to approximate that fire growth process. We as fire engineers can't take the time to burn everything and try to characterize everything under the sun, because ultimately, even if I take a fuel package and I burn it under a calorimetry hood, that might not be the exact fire curve I get when I put it in a compartment, right? But at the same time, we need to understand that the models we use to approximate fire growth are also intimately linked to the assumptions we make about the fundamental physics driving the problems. And so as part of this, we did a little demonstration on, as for something as simple as the upholstered chairs we were looking at, if you identify the regions of which different mechanisms of fire growth affect that process, we can better fit that data to mathematical models that actually match the physics, right? And again, use of that in sort of an engineering context, we might need something more complex, we might need something more simple, but that's sort of the core idea, is understanding that's the kind of drivers that affect this process of fire growth. So as an engineering community, as we continue to use things like fire growth in engineering, I think it's worth just taking a second to sort of analyze what are the assumptions that we're making, particularly with our traditional methods for representing fire growth, and what knowledge gaps are there as we continue to explore this topic more in the future. And so before we wrap up, I just wanted to quickly do some acknowledgements. I want to thank everyone for burning all those upholstered chairs. There was a ton of people involved in that project. So I want to say thank you to Ian, Johnny, Angus, and Rory from the University of Edinburgh. There was an ongoing project where we've been burning mattresses. And so you saw one of those cases where we're looking at the alpha T squared fit of that mattress fire. So I want to thank Vladimir Moser and Milan from CVUT in Prague. And thank you to the SFP Foundation. When during my PhD, they provided financial support for burning all those chairs. So I do really appreciate the foundation and all their efforts. And with that, I will take any questions. Thank you.
We'll speak through your microphone. Thank you very much, David. Great presentation. I thoroughly enjoyed it. I think it has some really interesting outcomes and thoughts for technical professionals within the built environment, trying to design some practical solutions. So now I'll open the floor up to any questions. I know there's probably one or two questions early on in the chat. If you wanted to have a look at those. Yeah, in the meantime, if anyone has any questions, feel free to turn your mic on and just ask away. Thank you.
If you see the chat, can you read them to me? Because I can't find it.
So there was a chat early on from Tash. If one is having any test reports on combustible elements, will the calculation be considered an idealized approach or an experimental approach?
That one there.
Yes.
Test reports of a combustible element with. Will the calculations be considered an idealized approach or no? That's interesting. Depends. I think it depends on how you use that information, right? So something that I would do when developing fire curves when I was working in industry was you can use something like the alpha t squared framework if you can make the assumption that the t squared dependency fits the sort of fire I'm trying to describe. You could use something like test reports or experimental data provided externally, and you can sort of fit that data to the growth rate of an idealized scenario, right? So the process of an idealized fire or real fire data is kind of a cyclical one, right? All of these idealized fire scenarios were informed by experimental data. The important part is just making sure that the underlying assumptions, right? Like, does the alpha t squared framework even make sense, are answered first. I hope that answers the question.
And then the second one just after that one.
Cool. What is the method generally used for total peak heat release rate prediction? Oh, there we go. Okay, so what is the total? How do you predict the total heat release rate based upon the combination of various combustible elements? And I think that is a $1 million question. If anyone can figure that out, please reach out because I would love to know the answer. But effectively, something to keep in mind is peak heat release rate is not an intrinsic property of a fuel package. I think that's really important to remember. The peak heat release rate is not a material property. It's not a product property. It is the manifestation of the competing burning rate per unit area, the actual area of burning, which that's controlled by things like flame spread and orientation of the solid, and the burning rate per unit area is a combination of external conditions and material properties and product properties and how those layers of materials might interact with one another. So actually, for trying to predict peak heat release rate, there's a lot of work that's been done on things like single homogeneous materials, taking stuff like cone calorimeter data and predicting that in very specific configurations. And even that starts to break down very quickly when you start adding any complexity, like physical mechanical failures of systems, like if you have skins that fail, like ACM, ACP materials. If you have things like certain charring materials where you have char layers that might slump off or delaminate, all of a sudden all those predictions go out the window. So trying to understand peak heat release rate behavior is a really complex process. I would try to rely on experimental data that's actually in configuration. So looking at an assembly as close to the end use configuration as possible, but still understanding even then, right, it's going to be linked to how you run that experiment. If I take a 3-seater couch, right, and I ignite it in the middle versus the side, right, they're going to result in two completely different peak heat release rates because of the rate of fire growth over that couch, right? So I think the important takeaway is I don't think it's safe to say that peak heat release rate is a fundamental property of a fuel package.
There doesn't appear to be any more questions, so feel free to unmute yourself. But in the meantime, David, I guess my sort of question is, what's the sort of main takeaway message you have for whether it's students, academics, or industry professionals who are on the call from this? Yeah, what's your main key message?
I mean, I think the main takeaway is understanding the process of things like fire growth and understanding the use of, let's say, more broadly, experimental data and the models that come from those experimental data. I think there are a wide range of uncertainties in that process. Not to say that we can't use these tools. As engineers, we still need to use tools to approximate things like fire growth. But I think it's worth taking a step, no matter what we're doing with these tools, and really analyzing the underlying assumptions, right? Are these models and tools that we're using fit for the purpose that we're using it for? And I think that goes beyond things like fire growth. That goes into things like using correlations or using even the more complex things like CFD, right? All of these tools, as complex as CFD or as simple as an alpha T squared fire, have many embedded assumptions into them. And I think it's worth really taking a step back and making sure we understand the limitations and consequences of those assumptions and make sure that we're choosing the best model we can for our purpose.
I have a sort of a follow-up question to that, and that how, when going to these more emerging, more complex hazards, as you mentioned, electric vehicles, cladding, mass timber, how do you sort of feel about using more traditional methods such as an alpha T squared?
Mm.
And how do you believe they fit into that, or whether they do or don't fit into that existing framework?
I think that's definitely a case by case basis. I think there are generic fuels that if you can show that it's controlled by the same sort of t time squared dependency by radial growth and things like that. I think irrespective of what that hazard might be, eventually, let's say it's composite materials and things like that, I think then all of a sudden the alpha T squared framework does work. So long as you consider also things like external heat fluxes and other things that might vary your alpha. Um, but I think when it comes to things like particularly battery fires, particularly cladding fires, and even mass timber, I guess it depends on the configuration of the timber. I think there's a lot more work we have to do before we can really say what are the simple models that we can approach those problems with.
And we just have one last question in the chat.
For compartment fire, could you comment on the variance of the fire growth rate for compartment fires? I mean, it's a interesting question. I think from experimental data that I've seen, right, it depends on a lot of factors. It depends on what is your for a compartment fire, you need to consider the compartment, right? So when we're looking at things like very open compartments where you have fuel limited conditions, you can look at things like traveling fire models and all sorts of approximations for understanding how that fire might grow within a sort of large open floor plan. But if you start looking at ventilation limited control fires, the growth rate will first be limited by the fuel, but then the compartment, things like the smoke layer, start to interact with that growth rate. It'll accelerate that growth rate, and eventually you'll probably reach a flashed over condition, in which sort of the entire framework of fire growth kind of goes out the window. So I think for compartment fires, it really is important to first take a step back and think about what kind of compartment am I looking at? Am I looking at sort of what we'll call our traditional regime one type fires, or we're looking at sort of compartments that sort of fit that flashover framework really well? Or are we looking at sort of more large open floor plans with large openings that fit more of a fuel controlled process? Because then if it's fuel controlled, then it's limited by the fire growth rate of your fuel. Then you're back to the drawing board of what is sort of my growth rates I might predict based upon my fuel load.
Excellent. Oh, sorry, looks like we have one question from Harriet.
Hi, David. Thanks for the talk. I was wondering, how did you know how many chairs you needed to burn? Is there a methodology or a consideration about when you've got you've captured enough of the outliers?
So the question is, sorry, David, how did you know how many chairs to burn? It was sort of, did you know when to burn the line?
That's an excellent question. Thank you, Harriet. That's a great question. And that's a very long answer, but I'll give you the short version of it. We had the chair project was part of a sort of a larger project that I initially conducted on some simpler experiments. So I ran a very large series of experiments on using cone calorimetry on very simple, just PMMA slabs. Hundreds of experiments conducted to basically determine how can you come up with an optimization point for determining once you establish what my level of confidence, my desired level of confidence is. We came up with a framework, and then we applied it to a more complex thing. Effectively, the whole question of how many chairs you need to burn or how many experiments you need to run is a really interesting question with a very complex answer. But it comes down to the most important question is not how many do I have to do, it's what level of confidence do I want in the results. And that will manifest itself in how many experiments you do. So for the chairs, for example, I was targeting a certain level of uncertainty in a specific metric. And I decided that actually, based on my preliminary calculations, about 25 was enough. And turned out I did actually end up converging to that level of statistical confidence with 25. So that's why that's how that number was chosen. Yeah, it's a great question, actually.
Thank you. That's super interesting. Thanks very much.
So it's just over 1:02 local time, so we might wrap up for today. I would like to thank Dr. David Morrisset very much for his time, his really interesting presentation. I know suddenly I myself has dipped my toes into both academia and consulting. There's some really insightful outcomes for both of them. The SFP chapter will be hosting a couple of presentations in late June and early July. We have the speakers confirmed, so please keep an eye out for that. In the meantime, I'd like to thank you all for your attendance and especially today. So thank you all and see you later.
Thanks, everyone.